In this video, we'll be talking more in depth about the 6 trigonometric functions. And what we want to start off with is this problem that just says to recall, we want to find cosine of theta and sine of theta given this triangle. So this is a right triangle, just to be clear. And we have the angle theta here with a side of y, a side of x, and a hypotenuse of 1. Okay, so in order to find cosine of theta, remember cosine of theta is equal to x over r, where x is the horizontal distance and r is the hypotenuse. Okay, so with that, in this case we have x over the hypotenuse is 1, gives us x over 1, which is just x. And I just want to be clear on this method. When we say cosine of theta equals x over r, that is only for this theta. If we had put theta up here, then cosine of theta would not be x over r. So this method of x over r, y over x, when we're talking about cosine, sine, and tangent, only works when theta is toward the origin. Okay, so with that in mind, now we have cosine of theta equals x, or x equals cosine of theta. From here, let's go ahead and do the same thing with sine of theta. And again, because theta is toward this origin, we can use the method that sine of theta is y over r, which gives us y over the hypotenuse is 1, y over 1, which is just y. So sine of theta is equal to y. Now, what if we went back to that problem and we took this length of 1, this hypotenuse, and we held it exactly in place and rotated it all the way around the origin, just like so, and created a circle of radius 1? Would the cosine of theta and sine of theta values change at all? The answer is no, they would not change. Cosine of theta would still be x, sine of theta would still be y. But notice what that tells us. Now we know how to find the location of this point on the circle. We have an angle theta, we have a unit circle, meaning a circle of radius 1, and we can find where the terminal side of that angle intersects the circle by just finding cosine of the angle for the x value of the circle, x value of the point on the circle, that is, and finding sine of theta for the y value of the point on that circle. So we end up getting that finding the point on a unit circle given an angle theta, we just find cosine of theta, comma, sine of theta, and that gives us our intersection point. It is very important that we remember this is only with the unit circle. It does change when you're dealing with circles of other radii. Okay, so with that in mind, now we can introduce the easier way to approach the 6 trigonometric functions. As mentioned previously, we used this x over r, y over x for tangent method, but this method only works for this origin angle here. What about if we wanted to find this angle up here, which we could call alpha? suddenly the x over r, y over x method no longer works for that angle. So we need another method. And our other method is one that you're probably more familiar with if you've ever studied trigonometry. It's called SOHCAHTOA. Okay, so SOHCAHTOA. Try to commit that to memory. It is so key. SOHCAHTOA says that sine of whatever angle you're dealing with is equal to the opposite over the hypotenuse, which is what we have right here. Sine of theta equals the opposite side of theta divided by the hypotenuse. Cosine is equal to the adjacent side of theta, hence CA, divided by the hypotenuse as well. And tangent is equal to the opposite of theta divided by the adjacent of theta, just like we have here. And the other three, again, can just be found using the reciprocals, so we don't have to memorize them. It's just something we always need to remember, that they are just the reciprocal identities of the original three trig functions. Okay, so committing this to memory is very, very important. SOHCAHTOA. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. And just to be very clear, when we say opposite and adjacent and hypotenuse, let's say we have some triangle. The opposite side we'll put in red here. So let's say we have some angle theta. The opposite of theta is this angle in this side in red. The adjacent of theta is the side connected to theta. See how theta is touching this side and the hypotenuse? Well, this side that it's touching that isn't the hypotenuse is the adjacent, which is in green. And finally, we have the hypotenuse, which is always the diagonal of your triangle, which we have in purple here. Okay, so sine would be the red side, the opposite, divided by the hypotenuse, the purple side. So let's go ahead and try this out. We want to find all 6 trig function values of angle B. So angle B is right here. And notice that our x over r, y over x method will not work here because we don't have a right triangle centered at the origin. The right angle always has to be connected away from the origin, like so. But in this case, if you were to draw it, it would look more like this, which does not work. So we have to use our SOHCAHTOA method. And SOHCAHTOA says sine of angle B is equal to the opposite side of B, which is 12, divided by the hypotenuse, which is 13. Cosine of B is the adjacent side, so the side touching the angle B, which is 5, divided by the hypotenuse, which is again 13. Tangent of B is the opposite over the adjacent. So the opposite is 12, the adjacent is 5. And now cosecant is the reciprocal of sine, so it's 13 over 12. Secant is the reciprocal of cosine, that's 13 over 5. And cotangent is the reciprocal of tangent, that is 5 over 12. We have very quickly just found all 6 trig function values by simply using SOHCAHTOA. Okay, so from here, let's go ahead and keep going with this. we're going to start introducing the major angles that we need to memorize for these trig functions. So before we start really getting into them, we should introduce a definition that says given theta is acute. So remember, acute means it's between 0 and 90 degrees. Given theta is acute, then sine of theta equals cosine of 90 degrees minus theta. And vice versa, cosine of theta is equal to sine of 90 degrees minus theta. Cosecant of theta is equal to 90 degrees minus theta. Secant of theta is equal to cosecant of 90 degrees minus theta. And you get it from here. Tangent and cotangent match together, just like sine and cosine, and secant and cosecant. So, what do we call these? These are our cofunction identities. Cofunction identities allow us to change the trig function we're dealing with. So if we're dealing with sine, we can change it to cosine. If we're dealing with secant, we can change to cosecant, and tangent to cotangent, which sometimes allows us to simplify the problem or cancel things out. It is a very useful process, and it helps us in memorizing some major angles that are about to come up in a few moments. So to start off with, we want to write sine of 30 degrees in terms of its cofunction. So sine matches with cosine. So changing sine of 30 degrees, we would get cosine of 90 degrees minus the angle we started with, which is 30 degrees, which gives us cosine of 60 degrees. So sine of 30 degrees is the same thing as cosine of 60 degrees. Okay, take a moment, see if you can't write tangent of 45 degrees in terms of its cofunction. Okay, so hopefully you gave that a try. Remember, you can always pause the video. So we have tangent of 45 degrees. Its cofunction is cotangent. So we're going to rewrite this as cotangent of 90 degrees minus the angle we started with, which was 45 degrees, which gives us cotangent of 45 degrees. So notice something odd here. Tangent of 45 degrees has the same value as cotangent of 45 degrees. They are interchangeable, really. All right, so let's keep going from here. And now we can introduce those major angles I was talking about. So if you remember that angle chart we've seen in a previous video, we had 5 major angles in quadrant 1 that we needed to commit to memory. 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And we could also write them in radian form. 0, pi over 6, pi over 4, pi over 3, pi over 2. We need to know their trig function values by heart. These come up so often that we need to commit these to memory. And really, you need to commit them to memory for that entire angle chart, all the way around the circle from 0 to 360 degrees or 0 to 2 pi, however you're measuring degrees or radians. But we're going to show why that cofunction identity formula was so useful, because it is difficult to memorize an entire list of angle values from the entire unit circle. So we'll be able to introduce a way to just memorize quadrant 1 and get everything else from there. Okay, so what this is saying is, when your angle is 0 degrees, sine of 0 degrees is equal to 0. Cosine of 0 degrees is equal to 1. Tangent of 0 degrees is equal to 0. From here, when we plug 30 degrees in for sine, we would get 1/2. 30 degrees in for cosine, we'd get the square root of 3 over 2. Tangent of 30 degrees would give us the square root of 3 over 3, and so on. There is one quick correction I want to make to this, though, and that's tangent of 90 degrees. Remember, tangent is sine divided by cosine. So if we take sine, which is 1 when we have 90 degrees, and divide it by cosine, which is 0, 1 divided by 0 is undefined. So tangent is undefined. There's a vertical asymptote there if you were to graph that. So these values are all very critical to commit to memory. So what if we wanted to find cotangent of 45 degrees? Well, using this chart, we know that with this chart and the cofunction identities, remember we said cotangent of 45 is the same thing as tangent of 45, and tangent of 45 is equal to 1, so cotangent of 45 degrees is just 1. From here, if we wanted to find cosine of 60 degrees, then we would just go to our table. Cosine of 60 degrees is just 1/2. Okay. Now from here, we say that reference angles can be used to find trig function values for quadrants 2 through 4. So remember, this is quadrant 1. We can use reference angles to find the trig function values in quadrants 2 through 4. All we have to do is find the reference angle, then make note of the original quadrant so we know whether the sign is positive or negative. So for instance, cosine of 240 degrees. Well, remember, 240 degrees, if we started to graph this, 240 degrees would be in quadrant 3. Remember, this is 90 degrees, 180 degrees, and 270 degrees. So it would have to be somewhere between 180 and 270. So since we're in quadrant 3, which we'll make note of, then our formula says we take our angle and we subtract 180 degrees from it to find the reference angle. So 240 minus 180 is 60 degrees. That is the reference angle, and we're in quadrant 3. Why is this quadrant 3 so important? Well, remember the all students take calculus? We are in quadrant 3 and we have cosine. So is this going to be positive or negative? Well, we know cosine is negative in quadrant 3. So cosine of 240 degrees is equal to the negative cosine of this reference angle, 60 degrees. So we get negative cosine of 60 degrees is 1/2. So negative 1/2. Cosine of 240 degrees is negative 1/2. I want you to take a moment, pause the video, see if you can't find sine of 315 degrees. Okay, so we're going to go about this the exact same way. We'll graph it first. Remember, this is angle 270. A complete rotation would bring us back to 360 degrees. So that means 315 degrees is right in quadrant 4. So since we're in quadrant 4, that means that sine is going to be negative, since only cosine is positive in quadrant 4. So we get sine of 315 degrees is equal to negative sine of, and now we need our reference angle. Remember our formula, when you're in quadrant 4, you take 360 degrees and subtract 315 degrees from it. You subtract your angle, which leaves us with 45 degrees. So sine of 315 degrees is equal to negative sine of 45 degrees, which gives us negative sine of 45 degrees is the square root of 2 over 2. So that is sine of 315 degrees. Okay, so from here, we can introduce our unit circle with all of our major angle values. So this is what I was mentioning earlier. This is something that it really is worth memorizing, but it is a tremendous amount of information to memorize. What this is saying is, for instance, when you're dealing with the angle 150 degrees, or 5 pi over 6, either way, then cosine of that angle is the x value of your coordinate, that's negative square root 3 over 2, and sine of that angle is positive 1/2. There is something very important to note about all of these values. Let's look at 30 degrees, 150 degrees, 210 degrees, and 330 degrees. Do you notice anything special about their cosine and sine values? Hopefully what you realized is that all of the x and y values are exactly the same, except the sign is different. So this is one way to commit these to memory. All you have to do is memorize, for instance, that at 30 degrees, you'll have the square root of 3 over 2, comma 1/2 for cosine and sine respectively. You're going to have the exact same thing at 150 degrees. But because cosine is negative in quadrant 2 and sine is positive, you'll put a negative with your cosine value. An easier way to commit this to memory is actually to deal with it in radians. Look at every radian that has a denominator of 6. All of them have the coordinate square root 3 over 2, comma 1/2. So if you remember that, the denominator being 6 means you have the point square root 3 over 2, comma 1/2, then all you have to do is remember where it's positive and negative. Where is cosine positive? Where is it negative? And the same for sine. And the same thing works for a denominator of 4. They all have the same coordinate value with different signs, positives and negatives, and with 3. Okay, from here, we have our quadrantal angles. When we deal with 0 or 2 pi, we have the point 1, comma 0. That just means that when your angle is 0, or if you've made a complete rotation around from 0 degrees, your cosine value is 1 because you've traveled a distance of 1 on the x-axis. And your sine value is 0 because you have not traveled up or down on the y-axis. And likewise, right here, when you're dealing with an angle of 90 degrees, your y value is 1, which means your sine value is 1, and your cosine value is 0 because you have not traveled a distance on the x-axis. Okay, so from here, we can continue on to our last slide of this video. We want to solve the triangle ABC given A is 30 degrees, C is 90 degrees, and side C is 4. So the first thing we should do is start plugging in our information. Since C is 90 degrees, we know this right angle has to be C. And from there, A and B can go wherever we want them to go. So I'm just going to go ahead and put A here and B here. And side C has to be opposite angle C. So we'll put it here on the hypotenuse. Side A is always opposite angle A here. And side B is opposite angle B. Whenever you deal with these triangles ABC, the sides are always the lowercase letters and they are always opposite their angles. So we have an angle of 30 degrees for A here. How can we start solving this from here? Well, the first thing that we can make note of is we know how to find this angle B. Because whenever you add up all the angles of a triangle, the result always has to be 180 degrees. So 30 degrees plus B plus 90 degrees has to equal 180 degrees. And if we subtract 30 degrees and 90 degrees from both sides, we get B equals 60 degrees. So let's plug that in over here with our given information. And now what else can we solve from here? Well, notice we were given angle 30, not angle 60. So you should always deal with the information you were given first if you have the ability to do so. So sine of that angle we were given, sine of 30 degrees, we said has to be equal to the opposite side of that angle 30, which is side A, divided by the hypotenuse, which is side C. But we know side C is equal to 4. And from here, if we multiply each side by 4, that will get rid of this 4 in the denominator over here, leaving us with A equals 4 times sine of 30 degrees. But do we know what sine of 30 degrees is? We do. That's from our table. Sine of 30 degrees, sorry, a little typo here. Sine of 30 degrees is equal to 1/2. So A is equal to 4 times 1/2, which is just 2. And now from here, we want to solve for side B. But remember, we don't want to use information we found in case there's a mistake in it. We always want to stick with given information. So again, we're going to use this angle of 30 degrees and this hypotenuse of 4. We do not want to use the side A that we just found, because if we made a mistake, then it's going to carry over to side B as well. So how can we connect this 30 degrees that we were given with this side B and this side of 4 that we were given? Well, notice if we take cosine of 30 degrees, then that would be equal to the adjacent of the 30 degrees, which is B, divided by the hypotenuse, which is 4. Again, multiplying each side by 4, the 4's will cancel out on the right, leaving us with B equals 4 times cosine of 30 degrees. And we know cosine of 30 degrees from our angle chart that we introduced earlier is equal to the square root of 3 over 2. And if we put this 4 over 1, we can cancel a factor of 2 from the numerator and denominator, leaving us with 2 over 1, giving us just 2 times the square root of 3 over 1 times 1, which we don't have to write if it's over 1. So b is equal to 2 times the square root of 3. And we have now completely solved that original triangle given just those 3 initial values. I did want to make one more note very quickly before the end of this video. When you are memorizing these values, think about the sign values. Notice something here. We start with 0, then we go to 1/2. So let me put this like so. 0, then 1/2, then the square root of 3 over 2, the square root of 2 over 2, then the square root of 3 over 2, and then 1. What if we rewrote every one of these with a denominator of 2? So 0 would still be 0 over 2. And then 1 would become 2 over 2. So from here, notice that we are starting with 0, then 1, then 2, then 3, and then the fraction goes away. So this is the only odd one out. So we just leave this as 1. But notice a way to memorize these values. Just keep a denominator of 2 and start with 0, 1, 2, 3. Always keep that in mind. It'll start with 0, go all the way to 3, and then you'll go back to 1. There are tons of ways to go about memorizing this, however you see fit, but this helps you memorize sine, and then just remember cosine works backwards. You start at 1, then 3, then 2, then 1, then 0. Just like we have here. 1, square root 3 over 2, square root 2 over 2, 1/2, and 0. And if we want to find cosine without even memorizing it, we could always use those cofunction values that we mentioned earlier. So if we memorize sine, for instance, let me rewrite this really quick. If we wanted to find cosine of 60 degrees and all we have memorized is sine, then if we remember our cofunctions, we have sine of 90 degrees minus the angle we were given as 60 is the same thing. Cosine of 60 is the same thing as sine of 90 minus 60, which means cosine of 60 is the same as sine of 30, which is 1/2. Notice we didn't even have to memorize the cosine value. All we needed to know was the sine value of that angle. So, however you find best to memorize it, these were just a few hints that might help some of you along with this.